morning, everyone. It's a pleasure to speak to you again. And today I'd like to present the topic for today's robotic solutions for automation in horticulture. And horticulture is a very broad term, and really what I'd like to focus on is on the soft fruit industry. And I realized that when I signed up for this seminar early this year, I haven't anticipated that I will be visiting Bonn, giving presentations. Other people in our team, like Mark, will also provide technical presentations. So for me, there was a bit of a challenge, how to pitch the content of this presentation. So what I thought to do to avoid repetitions and presenting again the same story, I thought to actually take a different angle, focus a little bit more on the application itself, because I know that the PhenoRob team is also working on technology that involves strawberry crop. So focus on that, look at characteristics of the domain, challenges, so opportunities for robotization and automation. And there will be a bit of technical content, but I'll try to keep it rather broad and focus also on barriers that are preventing a wider adoption of robotics in the sector. I hope also that this talk will be complementary to what will be presented immediately after, so on adoption of upscaling robotics in agriculture. So yeah, this is a short overview of my presentation. I'll first talk a little bit about why soft industry is important and what we can actually learn, what are the drivers for adoption of robotics, and then show key robotic applications that involve critical operations in soft fruit industry, like fruit picking, transportation, plant treatment, and so on. And then finally, the final part, I will focus on what are the barriers for adoption of robotics technology in the sector. So soft fruit industry that includes strawberries, raspberries, and other berries is an important part of the global economy. So strawberries, for example, are very healthy, high value crops, so it's important for economy. And strawberries are grown worldwide. So what we can see here on this image above is the distribution of different species of strawberries, showing that we've got quite high presence in Northern America, Europe, and Asia. It doesn't necessarily, so it's not all the continents have equal representation, but it shows that it's actually in mid-temperate climates, this is a very popular crop. And if we actually look at who is the biggest producer, then this pie chart below shows that actually China has got 42% of the total strawberry production. USA, or basically California, holds 16, and then we've got countries like Mexico, Egypt, and so on. Germany, UK, we can see that this is fairly small percentage of the total production, but I think there are some interesting stats that will allow us to interpolate and show how relevant is that industry to robotization. So, for example, in UK, the market is worth 630 million pounds a year. So this is soft fruit covers 1/5 of all the fruit produced. And I think the interesting bit is that these figures, if you take these figures, you'll be able then to extrapolate, for example, how many, theoretically, how many robotic units you would need to fully automate the, for example, picking strawberry picking operations. So, for example, assuming some average efficiency of the single robot, 30 tons per year, that results in sort of 3,000-5,000 units, depending how you count. So that shows you the potential. So for a single country, that's already quite significant. When you take into account that this is 1.5% of the global market, that shows you that the potential for introducing robots is you know, the ceiling, the maximum is very high. Strawberries are grown in different ways in different parts of the world. So we've got systems where the strawberries grow on the ground, on beds. So this is very popular in California, but in countries where the conditions are not as favorable, then there are these modern solutions where the strawberries are grown under the tunnels and even on tabletops. So for example, in the UK, majority of production actually happens on the tabletops. And some of these varieties and systems are more suitable for automation. So you can see that these tabletops are particularly suited because the systems were designed to actually maximize and simplify human picking operations. And I think this picture here shows really the first of all, how does the real strawberry production site looks like, but also how challenging that task is. We can see how many of these berries are, how densely they are packed, and also that only some of them are ready to be picked. So the person who is picking has to be very dexterous, mentally switched on, and very actually, you know, very fit to perform this task. So drivers for adoption of robotic solutions in horticulture and are more or less the same as in the entire agriculture. So the main driver is the labor shortages, and typically agricultural sector, for example, in European countries, relies on migrant workers who come and work typically through the season, and due to social political pressures, this is an unsustainable direction, and these are not well-paid jobs. Local people do not want to take them, and for example, in the UK, this is a big issue. So following, you know, Brexit and leaving the common market, UK now has to rely on visas, which are not there. The procedures are very complicated, and that really sort of puts the sector under pressure. And I could see the change of narrative when it comes to robotization of agriculture. Like if you would speak to people 10 years ago, they would be saying, "Oh, robots are going to take our jobs." Now farmers come back and say, "Oh, we hope that robots will save our jobs." So you can see that there is a big shift in narrative when it comes to robotics. Second aspect, maybe less, but still very important, is the sustainability. So lots of agriculture or horticulture production is relying on chemicals for crop protection and care. And, you know, for example, on this graph, we see what happens to the resistance of different plants or weed species to different chemicals over years. So it is, you know, the problem plants are becoming more resistant. It's becoming more expensive to develop these chemicals. So this is a big issue. There is a big carbon footprint that is associated with agriculture production and so on. So these are the main drivers, and hence, so in result, we team up with the other colleagues in academia, tech industry, so robot manufacturers and growers, and we started a set of projects which we call as an umbrella project, robotic and autonomous systems for berry production. And we started a number of projects which look at different applications and technologies that will eventually lead to automation of the soft fruit industry. So we wrote this overview article in the 2018 that lists the possible applications and relevant technologies. So I will now go through these applications individually, and we shall see what are these characteristics. But before that, all of these applications that are listed there will require mobile autonomy. So in our case, mobile autonomy is a key enabler of all these applications. And over the past, 5-6 years, we've developed a system, autonomous system for navigation of robots in agricultural environments, and for example, like polytunnels. And the whole system is based on topological representation, which allows first scalable decomposition of space, efficient operations, localization of agents, efficient route planning, adapting different behaviors to the situation, and then on the highest level, on robotic allows coordination of the fleets, simulation and modeling of the system. So it's a very effective approach, which we which we demonstrated in different applications and submitted a paper which is currently under review. And from all these experiences, we've identified a set of challenges that were not really known to us before we started this project. So we've got very narrow spaces in polytunnels, so navigation is not as simple as one would think. You cannot rely on typical sensors like GNSS because they are not very reliable. There are some issues with aliasing, localization errors, and so on. So this is all sort of, these challenges also set the future directions of our work and our projects. The holy grail, you could say, of automation in horticulture is fruit picking. And that obviously a majority of cost associated with strawberry or soft fruit production is related to harvest. That has to be, I already mentioned what skills are required, and any sort of automated solution has to face the reference, which is the current human rate. So this is a typical performance of a person, of a skilled picker in the UK system, which is around up to 30 kilos per hour, and any solution that is proposed has to match that. Mechanical harvesters were quite popular in the 90s, especially in the US, but they were not very selective. They were not suitable for fresh fruit, and they were not very economical. So it seems that that was a failed attempt at automating harvesting. Recently, there is a lot of interest in the robotic startup space in different parts of the world due to the drivers that I mentioned before. So there is so now again the industry and academia tries to tackle this task of fruit picking with new tools, AI, perception, better understanding of robotic components. And then if you these are some examples of the solutions already being proposed. But when you look at the details, you actually discover that there are no commercial solutions available for fruit picking yet. And we work with these companies, and it's quite clear that not only that the problem is technically complex, but it seems that it's beyond a single company. Or ability for a single company to develop entire solution, because it's unlikely that a single robot actually will solve a fruit picking problem. That needs to be a system of systems. So picking, logistics, transportation, farm infrastructure, all these issues have to be taken into account and to lead to actually successful system. I think I'll skip these slides and I'll go directly to the next task, which is in-field transportation. I mentioned already that logistics tasks are big part of the operation. Human pickers spend around up to 20% of the time transporting the crates with fruit. There is also some need for infrastructure. So, for example, up to 10% of the field area might need to be used for transportation. So, access roads for large vehicles, tractors, and the important thing is that picked fruit needs to be stored in a cool store very quickly, so it cannot really stay at the field. It has to be taken as soon as possible, because any extra hour that the fruit spends in the field reduces its shelf life. So it's very important. So that's where you can make a big change. And then through our projects, we've developed a system that actually it's a robotic system that aids human pickers and provides the transportation service. So whenever the picker is ready, can call the robot, and the first available robot comes, picks the full tray, brings the empty one, and in that way this robotic system supports can optimize the workflow. So we've demonstrated that in the tunnel scenario. The group from UC Davis, which I visited a couple of weeks ago, they've developed a system for open fields. It's got very similar principles. So the human picker is tracked. Actually, what is being tracked is the cart, as in this case, and then they propose a very low-cost solution that, but that the function of the system is more or less the same. Next task is plant treatment. So these are operations that typically need to be performed on regular basis. So big potential for robotics. For example, a big issue in polytunnel production is powdery mildew, and this fungal disease typically is treated with use of some chemicals, and there is some good evidence that by using UVC light, or this is called light treatment, and applying a specific dose, you can reduce the presence and occurrence of powdery mildew. It seems also this light treatment is good for other type of issues, diseases, and for other type of crops. So it's a very good application. It's a very harmful operation to perform for people, hence it's a perfect application for to be deployed on the robots. And we work together with our partners on the solution that looks like this. So it's a Thorvald robot with the UVC lamps, and basically the robot just drives very slowly at the specific speed, traverses and basically light treats the crop. Finally, we've got monitoring and forecasting. So these are forecasting is super important for farmers because it's the tool to really fight with supermarkets, get a good deal, reduce waste and plan labor. And many of the current ways of forecasting the yield and what to expect at the harvest time is based still on intuition. So, for example, a couple of years ago, there was the case that 30% of UK growers could get it within any acceptable accuracy for weekly forecasts. So one of the key difficulties here is that to make a precise forecast, you really need to understand at what state your crop is. So how many flowers you've got, how many berries are unripe, how many of them are ripe, and so on. So former student of mine set up a startup which tackles that problem, which is called Fruitcast, and basically he develops techniques for tracking individual berries, and this way he can count each different type or each different stage of growth of the berries, and that can be done from a mobile platform, like from a robot or from a handheld device. Good. And so the final part of this presentation, I'd like to focus a little bit on technical barriers for adoption and of robotics. And one of the things that we've learned from these projects is that when it comes to individual components that perform, I don't know, perception, picking, grasping, gripper design, or some automation solutions, each of these solutions on their own can be pretty good, demonstrated in isolation, but when you put it together, the entire system is not very robust, and that requires actually significant investment and effort in the space that it's maybe it's not very clear who should address that issue. So this famous valley of death between academia and industry for any technology really, and which requires really a lot of investment and effort to actually bring particular technology to a economically viable solution that makes sense, and it seems that this is a particularly difficult in agriculture, where the amount of investment is still not there yet, and that's one of the barriers. Who will actually work on the robustness of that technology? There is of course cost. If you've got one of these robotic pickers, sensors on their own can be half of the price. Issues of scalability, how we can deploy these systems at scale, how we can manage the fleets, how we develop the farm and robot infrastructure, and then big barrier of safety, which still, for example, under current regulations, robots still need human companions, which completely destroys the economic case, and there is a still lack of regulations of operation of agricultural robots in agriculture. And finally, I skipped a set of slides which elaborate a little bit more on these barriers. I'd like to maybe now wrap it up and mention other barriers of adoption, which is the result of the review undertaken by my colleague and boss, Simon Pearson, who looks at the sort of a big picture of deployment of robots in different areas of agriculture. So he wrote a review, which is basically a paper to inform UK government about the challenges and potential automation in horticulture. And the key issues that he identified through his research is that there is still a lack of capital and confidence to invest in agricultural robots, and that's maybe this could be attributed to the fact that there really isn't many successful utilizations of robots in agriculture, definitely not in horticulture. So these are still demonstrators, sometimes very impressive, but not yet economically viable. He also identifies that the area of development is populated by rather small actors that are, so for example, startups that are trying many different things. They might be very good in specific technological aspect, let's say picking or autonomy, but none of them has got volume and ability to develop the entire system. So and there is also lots of repetition. So companies, due to IP protection, they tend to repeat exactly the same developments as others, and it seems that this is a big barrier, because that actually prevents the entire sector of from developing useful solutions. So we are now working with the companies on ideas, how we can develop, at least on the software side, on some standards that would be useful and could be shared between them. There is still big question about what is the right business model. Are we going to sell robots, or should that be really provided as a service? Who should actually sell the robots? Should that be the company who manufacture, or rather some integrator specialized in these solutions and understanding the entire pipeline? And then there is a big gap in education and training, and initiatives undertaken by PhenoRob, University of Lincoln, in actually training the next generation of PhDs. These are early signs that this situation is changing, but that training also has to go to other areas beyond academia, or beyond higher education, and so this is still work in progress, and it's likely that adoption of robots in agriculture and horticulture will first start with systems that actually do not perform the ultimate task, which is the selective harvesting, because this is super difficult, but the potential actually to make something economically viable is in this application that will augment the workers. So transportation system, crop care, forecasting. So there is a big hope that this will be the applications that bring the most benefits. And I think I'd like to finish at that note and discuss with the audience, different aspects of robotization in horticulture.